vacuum tube is the fundamental element in modern radio communication.
To learn the concepts behind a triode, it can be useful to learn the concepts behind a diode, which is a simplified triode without an extra component. The diode consists of these components: a positively charged metal plate called the anode, a negatively charged plate called the cathode, and a heated filament below the cathode, which typically runs in the range of 1.2 amps to reach a high temperature. Here is a diagram of the anode and the cathode. Fermionic emission is the process where electrons are released from the cathode by heating from the heater here. So when this has a current running through it, electrons in this cathode will receive enough energy to exceed the work function of the cathode and be emitted into the space between the cathode and the anode. And as this is positively charged, the electrons will be attracted to the anode, causing a flow of current between the two electrodes.
Okay, so the cathode is heated using a filament which causes the electrons to gain energy. Once they have enough energy, known as the work function, to liberate the atom, they move to the anode. This is known as fermionic emission. Thermo meaning heat, ions referring to the charges, and emission referring to them leaving the atom. Then we have a law known as Richardson's law, which states that the fermionic current density, which is the current density at the anode, is proportional to both the temperature and a factor known as the Boltzmann factor. This factor comes from statistical physics and can be interpreted as the distribution of velocities. And so we can see at higher temperatures, the mean velocity of the electrons is higher than at lower temperatures. This corresponds to the velocity, the electrons having more velocity to be able to reach the anode, which is going to increase the current density. However, for a typical triode, we usually need temperatures up to 1000 Kelvin, making them very inefficient.
Okay, so in the triode we want to maximise the fermionic current for a set temperature, because further increases in the temperature would lead to larger inefficiencies. So to do that, we can decrease the work function in the Boltzmann factor, which will in turn increase the Boltzmann factor. This causes a larger fermionic current through the cathode and the anode for a set temperature. Another thing we can do is encase this in a vacuum, which stops air molecules from outside the tube interacting with the electrons. This increases the fermionic current. So, from our diagram of the diode with the two electrodes, we can simply convert this into a triode by adding a control grid, which is a metal grid with a potential difference across it, which will affect the fermionic current between our two electrodes. With a positive potential difference on this grid, it will accelerate the electrons emitted from the cathode towards the anode, which will in effect amplify the original current that would have flowed through the diode. Whereas if we added a negative potential difference across this grid, it would repel the electrons back down from the control grid back to the cathode. This can be used for switching by completely blocking the electrons that are going towards the anode from the cathode. So from this diagram we can see the effect on the anode current when we apply different voltages to the grid. This is starting with a 0 volt potential difference on the grid, going down to a -4 volts on the grid. The cut-off bias is a term used when no current will actually flow between this, which would mean that this anode current would be 0, so it would be below -4 volts on this diagram. This can allow the triode to act as a switch, because it can completely block the current passing through the junction with just this small control grid added. This is a triode, which you can see here. Internally, it's just a cathode through the centre, surrounded by the metal grid, and then further surrounded by the positively charged anode. These are quite large and have been replaced with the NPN transistor, which we will now talk about.
Okay, so from the triode valve, we're considering the electrons as purely classical particles. But in order to transition to a solid state model, we need to consider the electrons as quantum entities. So in order to do that, we use the Sommerfeld model, which from quantum mechanics, the electrons can act as waves and as particles. And so they're essentially a wave in a finite box. And it's the interaction of these wave equations in this finite box that gives rise to what we call bands. And these bands can, at high atomic separation, these bands are quite high, and these generally correspond to insulators. Whereas when the bands are quite small, these are semiconductor materials, and overlapping bands are metals. So from quantum mechanics, from before we had the Boltzmann factor, which was used for the triode valve, but now we can't use just what we call the Boltzmann approximation. We have to use the full Fermi-Dirac distribution function from quantum mechanics. And here we have the valence band and conduction band. Okay, so we use the full Fermi-Dirac function because now we're dealing with energies that are a lot lower than what was used in the triode valve. For the triode valve, we were using temperatures of up to 1000 Kelvin. So in that case, where the work function is equal to E minus the Fermi level, this function approximates to the Boltzmann approximation. But now we're considering energies a lot lower. We need to use, from quantum mechanics, the full function. And this gives rise to something called the conduction band, the Fermi level, and the valence band. So the Fermi level is an imaginary level at which the occupancy function is a half. It doesn't necessarily have to lie between the conduction and the valence bands, but it is always equal to half. At equilibrium, at 0 Kelvin, it is between the two bands. And generally conduction can't occur for any electron in the valence band because they're all locked into these finite states. And the Pauli exclusion principle means that they can't really enter any other state because they can't be scattered. Each electron can't have the same quantum numbers, like 2 electrons, and so they can't be scattered out of these states very easily.
Right, so in this model, this is all relevant for an intrinsic semiconductor, which is a conductor made solely of silicon, where the Fermi level will lie straight in the middle at equilibrium. Now we have an extrinsic semiconductor, which adds either a group 3 element or a group 5 element. A group 5 element will become an electron donor, as it will have 3 electrons to add to the lattice, whereas a group 3 atom will be an electron acceptor by adding holes in its lattice for electrons to join. These are called extrinsic semiconductors. So, we have a p-type, which is denoted by the type that are electron acceptors, where their Fermi level is lower than what we have mentioned over here, because there is a low chance of electrons being free and being in the conduction band because there is an abundance of holes in the p-type, whereas the group 5 dopants cause this n-type to form, where the Fermi level is higher because there's a higher chance of the electrons being in the conduction band in this material. Now we can join them in what we call a p-n junction. And note that their Fermi levels will line up. So when these two types of silicon line up and their Fermi levels match, we'll now have a transfer via diffusion of electrons from the n-type and holes from the p-type. So it would sort of look like this. You'd have holes moving out of here and electrons moving into here. So then you'd get a region here, which I'll just draw over here, which we call the depletion region, where the holes have diffused across and combined with electrons in this half. They would then leave behind a negative charge in the form of ionized dopants in this half of the depletion region. And then the electrons that have moved out of the n-type would then leave behind positive regions as holes in this side of the depletion region. So at thermal equilibrium, the p-n junction will have this depletion region, which will need an electric field applied across the p-n junction to overcome.
Here we have the p-n junction under equilibrium. So the electrons cannot diffuse across the junction because they're repelled by the depletion region's electric field. It's causing them to be in equilibrium because they can't get across the barrier. But if we consider the case where we apply a reverse bias, which means the p side is negative and the n side is positive, what they're going to do is these electrons on the n-type are going to experience a force to the right, and the holes on the p side are going to be pushed towards the left. So essentially there's not going to be any current flow between the regions, and the corresponding potential, the built-in voltage, is going to increase. So there's not going to be any current flow or very small current flow in this system. Whereas if we then apply a forward bias, so the reverse, where the p side is positive and the n side is negative, it's kind of going to do the reverse. We're going to have a lower built-in voltage, so a lower amount of energy really that's required to overcome the barrier. The depletion region is going to decrease, and we're going to have electrons attracted to this side, and so there's going to be a strong current flow. So we can see that in one case we have very little current flow, in one case we have high current flow, which is similar to the triode, where it can act as a switch, where we had lots of electrons moving towards the anode.
From our previous section, we saw p-n junctions and forward and reverse biases, which we can now apply by sandwiching an n-type, a p-type and an n-type silicon together into this NPN transistor. Here we have the band diagram of the three types together, which you can see. This is the conduction band, this is the valence band for all three, and the Fermi levels in red, which you can see because the emitter is highly doped compared to the collector, the Fermi level is much higher. And in this p-type, the p-type has lots of holes rather than an abundance of electrons, which means that the Fermi level is lower. So when you pump holes into this p-type by applying a current to the base, this causes diffusion of holes into this n-type, which in turn causes the diffusion of electrons into the base from that n-type, which this p-type needs to be thin so that the minority carrier lifetime of the electrons that diffuse is lower, which allows them to drift across here rather than recombining into this base. The electrons are aided in moving across this depletion region by the ionized dopants on this side of the depletion region, and the anode, the positive anode, connected to this n-type. Note that this transistor will only work to a certain size, which is around 5 nanometers, because at this point the electrons will start quantum tunneling through the depletion regions, which will cause reverse current through this section and forward current through this section without control through the base. So this section being forward biased allows a high current to flow when a lot of holes are injected into here, and this reverse bias blocks current from flowing this way. Okay. And then now we can compare the triode to the bipolar junction transistor, and we can see the triode uses the one carrier, which is the electrons. It uses a high temperature, it's very large and inefficient. It works upon classical concepts and fermionic emission, whereas the bipolar junction transistor works with two minority charge carriers, the holes and the electrons. It doesn't work with these high temperatures, so we must use Fermi-Dirac occupancy, and it's only limited by its size. They're very efficient by using these quantum effects and relying on diffusion and drift.